Hi. We're going to convert a Gregorian year number to the closest matching Chinese zodiac animal. And we have to be careful because the proleptic Gregorian calendar doesn't have a year 0. Now, there are various ways that we could scrape the data off the website. However, I'm not going to go into that now. I have defined a matrix which corresponds to the table that is on the website, including being a little bit, should we say, dirty. So the first thing we're going to do is that we're going to clean this up a bit so we have some raw data that we can work on. We don't actually need all the columns, so we're going to index into this and choose columns 1 and 4. Those are the year numbers. But notice the spacing here, they're actually given as text. And then we are going to take the animal names, which are columns 2 and 5, skipping the empty column 4, which was apparently just there for spacing. Now that's all very nice, but we can see here there are at least spaces at the end of the rooster, and there are also spaces at the end of the years. That's not so much fun. So what we can do is we can do a without. This is like a set difference function on each of these with space. So removing spaces from them all, since there are no internal spaces we need to worry about. That looks better. Now we can transpose it. And that gives us the reading order is a bit better. But we still have 2 rows for each thing. So we're going to reshape this. We only want 2 rows in total, one for the years and one for the names. So that's going to be 2 row, 12 columns, reshape. So this is Greek row for reshape. And that gives us a much nicer looking table. It's also in backwards order, so let's mirror it. And finally, it's a matrix, but we would rather have 2 lists. So we're going to split this into a vector of vectors, and we can see that we have this, even though it goes beyond the screen, 2 vectors. And now we can assign this. We assign the first one are the years, and the second ones are the signs. And now we have the years separately and the signs separately, but the years are not numeric. We could do something about that, but it's not actually necessary. We really just want and the signs, because it's very easy to generate these year numbers as well. You can just do 2016 plus iota 12, where iota generates a sequence of numbers from 1 onto that number, and then we have the years. Okay, let's get started. We're going on a 12-year cycle. Oh, it's actually not even 2016, it should be 2006, but that doesn't matter. We're going on a 12-year cycle, and it would be nice to know where the origin point is for these. So we can see, say, the 12 divides these numbers. How much is the remainder? And then we can see there's 1 where there's no remainder, so it's evenly divisible. We can identify that one by comparing to 0. And there's exactly 1, and then we can find its index. It's index 10. So it's an index 10, and we start with index 1. That means there we have an offset by 9. If we didn't start with this 2007, if we started 9 years later, then we would be better off. So we can do a rotation. So the same symbol that means the mirror. If we use it with an argument on the left, it means a rotation, a cyclic moving of the elements. So we're going to rotate by 9 steps the signs. Now we start off with the monkey. So If a year is divisible by 12, then it's the monkey, and if it's divisible by if you divide it by 12, there's 1 left over, then it's the rooster, and then if there's 2 left over, it's the dog, and so up until 11 left over. We need this data into our function, and it's a little bit awkward to have it like this. We could transform it into an APL expression that generates this vector of character vectors, and we have a user command called wrapper that will do that for us. It's still very verbose though, so I think it's more fun to pack it all together. This is the enlist function. It just takes all the characters and jams them into a single character vector. That can fit on the screen at least. And once we have this, then we just need to know how to expand this into our full vector of character vectors that we need to select from. Notice that all these names begin with an uppercase character, and that's actually really useful. If we look for membership into, and here's a special system variable called quade, or the alphabet. So this is just a character vector containing the alphabet. And if we look for every character here is membership of this is the uppercase alphabet, I should say, then we can see that we get a 1 for the leading characters in each of these. Now, we can transform this function into a so-called train or fork, which means that we are referring to the arguments just in terms of function application. This is membership, and we want to use this membership to partition the left argument. So this points at the left argument. So this is the membership partitions the left argument. And then we reconstitute this. So every time there's a 1, we start a new section or segment. Every time there's a 0, we just continue the previous segment. So this is a more dense way of writing the same array, although we might need parentheses around it. Like this. And now, what we could do is we could rotate then by the division remainder when 12 divides the year, let's say 2018. Oops, what's going on? Oh, yeah, of course. The problem is that the rotation takes the argument. Remember, we had the 9 rotate. It takes the argument on the left. So we need to swap the argument. So this higher order function or operator takes this function and swaps its arguments such that the rotation amount is on the right and the data is on the left. Okay, so now we've rotated it to be Doug. And if we look at our original table, then we can see that 2018 is indeed the dog. So that fits. So we got the right amount. However, we don't want the entire thing. We just want the first one. So this selects the first one, and that gives us our dog. So this is the solution for the basic calendar. Here's a cool thing. We took the remainder and divided by 12, but there are also only 12 elements in this list of animals, which means if we rotate 12 times, then we come back to where we started. And it also means that any multiple of 12 gets us back to where we started. And the only thing that actually matters in the rotation amount is the remainder when divided by 12. So there's no reason to even compute that. Because if you just rotate it over and over and over again, then we get back to the to where we started, and when the last remainder that's less than 12 is what actually gets us to a new position. So this works as well. And it's not even inefficient because the APL system itself will compute what the final result will be. We don't need to do it for it. Now here's one issue then, and that is that when we get down to the the small numbers, when you get to 1, so that's the division remainder for 1. If we subtract one more, we get down to 0, but there's no year 0. So the animal that we would give year 0 actually needs to be given to year -1. In other words, if we have a negative year number, then we need to add 1. So let's say we have some negative numbers, and we don't have any 0, that will never appear, but we do have some positive numbers as well. Then we can compare this to 0. So if 0 is less than that, and then in order to make this a single function, we bind or compose the left argument to the greater than function. And this gives us a 1, or true, for all the negative numbers, and a 0 for the positive numbers. If we then take the right argument, remember this is this pointing thing, just like we had up here, that we had the little finger that points to the left for the left argument. So this is pointing to the right for the right argument. And we add that to the result of this comparison, then effectively we increment negative numbers, adjusting them back as if the calendar had a year 0. So if we use this instead of the actual year number, then we've compensated for the lack of a year 0. Okay, so we take this whole formula here and we put it on the left. And that means that we have the year number over here, and we don't even need parentheses because APL functions have long right scope. So this is the negativeness added to the year itself. We use that to rotate this entire thing, which computes this 12-element list of names, and then we choose the first one after we have rotated them into place, and this will be our function. It's a bit long to see here, but now we can say 2018, and we can also say year 1, and we can say year -1, and we can look at our table up here that F is the rooster, and the year before that, year 1 we said was the rooster, and year -1 should then be the monkey, and that is exactly what we got. So this is a solution to the problem. You probably don't actually want to write it like this. It would be nicer to have this thing saved as a constant. So let's try that. We will save this as our list of signs, and then we can just go up and say the list is this. And now we can use the function f exactly the same way. There's no difference here. It's just, in fact, the definition becomes the same thing because we take the value and substitute it in, but it's a bit easier to see. Thank you for watching.